Here's a quick answer to question 2 from the week 3 quiz. So here's the information given. We're told this is a probability density function for that follows a normal distribution for a random variable q. And so here is the function actually being graphed. On the x-axis we've got values ranging between 40 and 110, and on the y-axis between 0 and 0.045. And the first question asks us to label each axis on the graph above. So when looking at a probability density function, it's showing you the relative probability of getting different values of the random variable. The values of the random variable are shown along this axis. So in this case, that's q. So this value here. And then it's called a probability density function. What is measured on the y-axis is the probability density. And what this tells us is that we're much more likely, because the probability density is higher, to get values in this kind of range than we are to get values down here in the 45 to 50 range where the probability density is very low. Similarly, the chances of seeing values out here in this range are relatively low in terms of their probability. Okay, part B. We're asked to estimate the following two moments of the distribution and briefly justify your answer for each. This question could have been simplified to just say estimate and briefly justify your answer for these things. Here I was just kind of adding the detail that these two things that we're looking below at, the mean and the variance, are sometimes referred to as moments of the distribution. So how do we estimate the mean for a normally distributed variable? Well, the mean is the average value, and for a normal distribution it coincides with the most common value, which will be where the probability density function has its maximum probability density. Look down and see what the value of the random variable is. It's 75. And seeing as there's a probability density function, it is looking at a population, so we should say that the mean of the population, mu, is equal to 75. How do we justify that? So remembering that the mean is the expected value of the variable, it's the average value. If we look at the normal distribution, it's symmetrical, so it's evenly balanced on either side, equally weighted on either side, and because the distribution is symmetrical, so I'm going to say symmetrical distribution, this means that the line of symmetry is equal to the mean, because it's going to be equally balanced on either side of that line of symmetry. So the weighting of the variable on this side is exactly the same as the weighting of the various values of the variable on that side, so the mean is smack bang in the middle. Now for the normal distribution, the mean, the mode and the median, which are all measures of central tendency, are identical. So we've talked briefly about why the mean is 75. When you're looking at a probability density function, the mode is always the most frequent value, so look for where the PDF has its maximum probability density, that's here, and the value down here will be the mode. And the median will be the value which is exactly in the middle when all the observations are listed in ascending order. So when you're looking at a PDF, remember that the area underneath it will always equal 1. So the median will be the value which has 0.5 on one side of it and 0.5 of the area on the other side. And again, because of the symmetry of this distribution, there must be 50% of the possible observations on the left-hand side below 75 and the other 50% on the right-hand side the median, 75. So I just point that out because some people's explanations here they were tending to justify why the median might be 75 or why the mode might be 75. I just point out that those things are all calculated in a slightly different way, although identical in this case. The final question wanted you to estimate the variance. So the variance measures the dispersion of the distribution, and this was a somewhat tricky question. It relied on you being able to identify or know that the normal distribution tends to span about 3 standard deviations either side of its mean. And by the time you have moved 3 standard deviations either side of the mean, there tends to be a very small chance of seeing observations out beyond there. I'll just quickly show you Appendix D from the textbook, which is showing a table of probabilities for the normal distribution, cumulative probabilities. It's on page 742. And so this is for a given value of z, which is measuring the number of standard deviations from the mean of the standard normal distribution, which is 0. It will tell you the probability of getting a z-score less than that. So this value 3 is one of the things I was just talking about. In the standard normal distribution, that score of 3 is 3 standard deviations above the mean. And when I look at this table down here, I'll look down this column for the first 2 digits of my z value. There's 3.0 down there. And in fact, I want to know what the probability is of getting less than 3.00. So there it is there. This table is telling me that the chance of getting a score that is less than 3 standard deviations above the mean is 99.87%. That means that there is a chance of getting more than that value of only 0.13%. So I don't know if that was the best elaboration ever of what this probability table is doing, but the conclusion, or what we've seen, is that the chances of getting a score above 3 standard deviations from the mean is very small. And because it's symmetrical, the same applies 3 standard deviations below the mean. Back here, the chance of getting a score in that range would also be equal to 0.13%. So back to the actual question. We now know that the normal distribution, you hardly see any observations outside of 3 standard deviations from the mean. So let's see from our mean, how far away is 3 standard deviations? Well, it seems like when we get out to about this range, we're not seeing very many observations at all because the probability density is very, very, very small. So it looks to me like that's roughly 1 standard deviation, that's roughly a second, that's roughly a third. And if that's a standard deviation, the difference between those two things is 10. That's the standard deviation. We can see it again here. There to there is 10. So down here with the variance, I would say something like, because the standard deviation spans roughly 3 standard deviations either side of its mean, it looks like the standard deviation here is approximately equal to 10, and we then want to find the variance, which is the square of the standard deviation, so it will be approximately equal to 10 squared, which is 100. Job done.